All right, so we're gonna dive in where most O Chem 2 classes start. Some of you are joining us. You're in an unfortunate O Chem 1 class where they're covering organometallics. If you are from O Chem 1, welcome, and I'm sorry. But usually this is an O Chem 2 topic, and I want to give you guys a quick overview about what's going on with organometallics because professors usually don't give a great idea about what you're really looking at. And so what we're going to start with is something that you have seen a lot of. All right, so the molecule on the left is an alkyl halide. You've seen a lot of this. And what I want to remind you is that alkyl halides are fantastic leaving groups. And the reason why they're fantastic leaving groups is because I want you to do something for me really quickly. I want you to pause the video and pull up a periodic table. All right. So if you have a periodic table in front of you, I just wanted you to take a quick look at it, and I want you to find bromine. And then I want you to take a look at carbon. And what you'll notice is that bromine is further right than carbon, and things that are further right on the periodic table are more electronegative. They want electrons more than things that are further to the left. And so therefore, bromine wants electrons more than carbon. And so the consequence of that is that in this bond right here, bromine is going to be pulling that electron density towards itself. And that allows bromine to pop off really, really easily. That's why bromine's a good leaving group. That's why halogens are good leaving groups. Partially, it's their electronegativity. Also, they make really stable ions in solution, but we don't care about that right now. So with that being said, you are going to be doing something pretty funky with alkyl halides in the organometallic section. For the first time, you're going to be starting to add metals that matter, that are going to have consequence. So up until this point, you've probably seen sodium, you've probably seen potassium, and those really don't matter in this class. They are useless. But if you have an alkyl halide, you are going to either add magnesium or you are going to add lithium. And so the reactions are a little bit different for both of these. So what I want you to know is that magnesium, it sandwiches itself between the carbon and the alkyl halide. And lithium, it's a lot easier. It just flat out replaces the alkyl halide. And so each one of these has their own unique name. The MGBR compound is a Grignard reagent after a dead French guy that nobody cares about unless they're an O Chem. And then the other one has a less fancy name. It's an organolithium. But here's the thing that professors don't really clue you guys in on. What I want you to notice is that in both cases, this bond and this bond right here, in both cases, carbon is directly attached to a metal. Carbon is directly attached either to magnesium or to lithium. This completely changes the chemistry of the carbon bond. Now, want you to look at your periodic table again. I hope you still have it up. Take a look at it. Find carbon, find magnesium, find carbon, find lithium. What you'll notice is that carbon is further to the right than either magnesium or lithium. Carbon is astronomically more electronegative than magnesium or lithium. And magnesium is a little bit further to the right. And so because it's a little bit further to the right, the difference in electronegativity isn't as great between it and carbon. So carbon is going to be pulling on those electrons in those bonds. Let's give it 2 arrows for magnesium. And since the electronegativity difference is greater for the lithium, let's give that 3 arrows. And so what I want you to notice here is that in both cases, carbon is getting a lot of electron density. It's getting electrons pulled towards it. And so with both of these things, you've completely changed the chemistry of it. Here in your alkyl halide, carbon lost electron density. It was more electropositive. But here it's getting that negative charge. And that has a massive consequence. The massive consequence of that is the way I want you guys to think about this is that no matter what, both of these compounds are essentially a carbon with a negative charge. Carbon pulls on those electrons so hard that it essentially owns the electrons in the bond. So no matter if you have a Grignard reagent or if you have an organolithium, it essentially, in both cases, is a carbon with a negative charge. And so as we go through the problems, that's how I kind of want you to look at it. It works for some people. It doesn't work for other people. But I want you to test it out. Keep that in mind, though. There's a negative charge there. And so, with that being said, here's the thing that they fail to mention right out of the gate. And I'm going to mention it right out of the gate for both of these. When you have a carbon with a negative charge from a Grignard reagent or an organolithium, I want you to remember that first and foremost, these compounds, they act as strong bases. They act as strong bases. And so remember, bases love hydrogen. They love hydrogen. And so if you have a strong base, it's going to go for hydrogen. Now, they only act as a strong base if you have sources of acidic hydrogen. So let's designate what that means. Let's say NH, OH, SH, or even a carbon-carbon triple bond with a hydrogen hanging off the end. So if you have any of those things on a molecule, organolithiums and Grignards are going to rip that hydrogen right off because they love hydrogen. They're strong bases. A distant second, so after wanting to act as strong bases, a distant second, these things act as strong nucleophiles. And so, again, they're going to prefer to act as strong bases. But if you don't have acidic hydrogens like these, they'll act as strong nucleophiles. And the crazy thing is that many of the reactions that you are going to be working with at the beginning of your semester 2 journey are them acting as strong nucleophiles. So your professors, they are going to try to trick you. They're going to throw in things that have OH, SH, or a hydrogen hanging off of a triple bond. Be watchful for those, because if you have a Grignard, if you have one of these, it's going to go for that hydrogen. But if you don't have one of those things, your Grignard is going to act as a strong nucleophile, which brings us full circle to the first big theme that we talked about at the beginning of this O Chem 2 unit. We talked about how strong nucleophiles, or nucleophiles just in general, if they are in the presence of a C double bond O, they are going to go straight for the carbon of that C double bond O. And so, if you'll notice this ketone right here, it doesn't have any acidic hydrogens on it. And so, therefore, if you added in a Grignard or an organolithium with it, the Grignard or organolithium couldn't act as a strong base. It would go down to number 2. It would act as a strong nucleophile. And so in the next sections, we're going to show how these compounds act as strong nucleophiles with things that don't have acidic hydrogens. The next video is going to be a really long one. We're going to hit all of the major reactions with C double bond O compounds. And I'll see you there.